I really like to thank everyone for taking the time to come to the talk. And I hope that we are going to have some kind of new ideas coming out from this kind of a seminar and discussions. I look forward to also learning from you as a mutual exchange. So I'm going to talk a little bit about today. The main topic is on material design, but I'm also aware that many of the people affiliated with this institution are strong, good in optimization. That's something actually I studied and I worked on at the very beginning part of my I would call the graduate study, and that's where I kind of come across with Michael more than 20 years working in this area called engineering optimization. So I decided to give you a little bit of history of my research and then go into the material design research, okay? So I think about the time when I was a PhD, we have this new paradigm called the simulation-based design coming up. And I'm listing here example that we worked a lot in the past is the car, automotive, structurals, system design problem. And in this kind of, under this kind of research, my focus has been on design under uncertainty. So I'm listing here some sources of uncertainty associated with manufacturing operation. So the goal of the design is try to mitigate this kind of uncertainty. But at the same time, what got me very interested in this uncertainty area is actually view design as a process that we keep optimizing our performance at the same time we're reducing the uncertainty. So to some extent, design by itself is not just like determining or optimized artifact. It is also an information seeking process that we continuously allocate resource for uncertainty reduction. And that actually become an important part of my work. So yesterday in Reming's talk, we talk about aleatoric and epistemic. So this kind of uncertainty with manufacturing operation, we call them aleatoric uncertainty. And on the other hand, the kind of uncertainty associated with the design process, we call them epistemic uncertainty, because when knowledge is gathered more, that kind of uncertainty can be reduced. So I also want to share with you the people had a huge influence on my research direction. So back to my PhD was in 1995. So at the time I was doing my PhD, this paper, I think this is the first paper in the design area by Professor Parkinson called The General Approach for Robust Optimal Design. And really opens my mind thinking about uncertainty around a simulation-based design. We have uncertainty comes from the noise. We also have the uncertainty of the design variable itself. So at the end, you're looking at using optimization, try to accomplish the design objective is associated with robustness, reliability, which is the tail, right, of the distribution. And in some cases, you could actually have a preference function to optimize your utility. So this could be solved using optimization methods. So I would kind of attribute to Alan Parkinson to be the first one who used optimization to solve this kind of problem. So inspired by his work, I focused on robust design in my thesis. It was on using this method for improve the quality of engineering decisions. And then later on, after I become a faculty myself, my group has been developing a range of methods associated with robust design, the reliability-based design. And a part of that is also a topic called the design of experiments. So here we design the experiments from the computer simulation, right? We decide what to sample. And furthermore, to 2010, we extended the design and uncertainty to topology optimization, which has a strong role in structural optimization. That's the focus I'm going to talk about today, is the structural optimization problems. So I've been collaborating with some of the software company, not from the research funding point of view, but more from like point of view passing my research results. So some of the methods like in the cell systems, the 3DS, they have this DOE, optimum design experiments. Actually, that code is contributed by my group. And then in the HyperWorks, which is a topology optimization code, we have give them the Sora method. So Sora is part of the HyperWorks that you can use. So the software contribution is important in terms of making impact to industry. The second method, which had a huge influence on my research, is this method we call the Gaussian process modeling, and some people call this spatial random process, right? So it has important impact because it provides uncertainty quantification for the situation that we have lack of data. So you can see that you have 4 data points. All this curve can pass these 4 data points. So there's huge amount of uncertainty associated with the place you don't have any data. And further build on that is the work we have been doing. We called using this method for model validation and the model uncertainty quantification. So that's where you have data coming from both experiments and the simulation. And the way we calibrated the model, I think in the past, was inspired by Kennedy O'Hagan's framework. His framework is a Bayesian calibration of computer model. He basically used 2 GP models in his framework. One GP is used to surrogate the computer simulation called the YM. Another GP is used to surrogate the bias function or the difference between experiments and the simulation. And GP are used because oftentimes in design, we run into the lack of data situation, right? Small data problem. So GP is very powerful for that. And so in our work, we published the methods which can use multi-response approach to reduce the identifiability. Identifiability means that the whole calibration, it's an inverse problem, okay? Inverse meaning you collect the data for the output of the response, you call YE, and you need to infer what is uncertainty in your model. So we have both calibration parameter as well as the bias function. Due to lack of knowledge, both are uncertain. So in order to calibrate or infer both, it's a huge statistical problem using Bayesian methods. So we use multi-response, and there's many different solutions. That's identifiability, right? There could be many different possible combinations that leads to the result that will match with your output. So we use multi-response approach, and more recently, we're working on multi-fidelity modeling, and for both multidisciplinary optimization and some other applications. And just for the past few years, we are exploring a very different approach for this kind of problem that I don't know whether we'll have time to get into today, but we will see. If I have time, I will briefly talk about that, which is much more efficient than this kind of Bayesian methods. We're using a latent variable GP approach that we're developing in our work. Another piece of work that had huge influence on my research is Don Jones' work called EGO, ERGO, or efficient optimization of expensive black box functions method. And the original form of this method actually is a similar idea, has a similar idea with Bayesian optimization. Bayesian optimization, if you look at the literature, was even created even early than when Don Jones published his work in 1998. So this kind of method is very good for black box kind of problem that you start with some samples, you use GP to fit the model, could be very nonlinear, and then you use uncertainty quantification, but now you have to balance both the need for reducing the uncertainty as well as the need for optimizing your function. So it's a design-driven methods, right? And they have a acquisition function to balance the needs from both sides. So a simplest form is integration of those 2 quantity. Then you decide where you should sample next. And then you can pick a sample or multiple sample. And this is going to be iteration. You goes on for multiple iteration and you get your result. So Don Jones is the one I would think in the engineering design area, that first one who showed that this method is very efficient to do global optimization. So when he first presented this work is under global optimization, and you can compare to genetic algorithm and those methods, and you will find that this method is much more efficient. Okay, so these are the several different works, and these days has a huge influence on my work. And I was thinking in these days, I'm still using this GP plus Bayesian optimization in many of the design activities that we have. So we developed a batch sampling. We further extend BO for robust design because now you have objective that's not just a deterministic function. It could have uncertainty or variation associated with that. And we're using the BO approach to reduce what we call epistemic uncertainty. Basically, each iteration, right, you're reducing the uncertainty in prediction And more recently, we're using mixed variable, latent variable, GP method to close the loop for problems that has inputs that could be categorical variable. And we found in material problem, there are many problems that we're facing, the decision is categorical. So how do we build the GP model? Originally is a smooth function, right? So how do we, and you Bayesian optimization need a smooth function to tell you what's the uncertainty. So when we have inputs which are categorical, now you imagine you have this joint design space that belongs to different design concept. So how do you do this maneuvering in the sampling in the space? That is the work that we have been working on and have been benefiting material design. So I'm showing you here some examples of a material system. Now we're coming to the discussion about the use of this method for material design. By definition, advanced material systems are those that formed by changing the constituents, like what element, material element you choose, composition, what's the percentage of those elements, as well as the architecture of the material. So here you can see that I'm listing only a few very representative examples in energy problem. So this is the additive manufacturing structure to build a new battery system. In the middle, you can see this is like a spring nodal structure that can really achieve very high supersonic performance behavior. And lastly, it is a medical application that you build this soft robots that can go into the human the blood vessels and clean up, the clots. So there's many application that we have to make a decision about what is a material as well as what is architecture. So this is the area that I found a lot of opportunity working with my colleagues. In material science at Northwestern, we have very strong material science program. So I've been working with them on we call design D material, that all the way from microelectronics, very low scale like nanotechnology, graphite CNC to MOF structure to composite structure. And here you can see that all this problem has decisions associated with some kind of architectural structure. Okay, some of them could be stochastic. On the right is the typical mechanical engineering kind of a material design problem that deal with the architecture design. We call metamaterial structure, for example, for solar cell energy absorption, for mechanical cloaking. I will show you example, as well as energy absorption. The boundary between these two domains is becoming blurred these days, that we are running to more problem these days. We need to design the material as well as the architecture concurrently. And that basically increases the dimensionality when we do optimization search. So my colleagues, people that I work with, that I actually put on my first slides, is a long list of people I work with in material mechanics. They work a lot on we call the forward problem, which is transformation of the information. So it's kind of cost-effect relationship from processing to structure to property and to performance. So you can imagine that we're building machine learning model, okay, for each of this mapping, trying to see whether I can find my laser pointer here. But yeah, for each of this circle, okay, processing to structure, structure to property, and property to performance is a transformation, okay? And we're actually helping them to build a machine learning model, but our interest is really the inverse problem, right? Given some kind of targets or requirements, how do we explore this large dimensional space very quickly? It is highly dimensional. I can tell you the options are billions or even more if you think about like how this, how you can design architecture, right? And if you want more precision, the dimensionality is much higher. So today I'm going to show you the methods that I've been developing in design and uncertainty throughout the years or the first stage of my career. In the past decade, we have been using them for material design. So some example of mapping or the terminology. So in the left, we call meta modeling or surrogate modeling. And now on the right, in material design area, we're doing machine learning as well as surrogate modeling and also feature extraction. or called feature engineering, right? Using AI and those methods, we can identify what are the important design features. Design experiments in the left now, it's called adaptive discovery in the material area, okay? And the multi-fidelity modeling in the material area we're doing, we call the multi-modal data fusion, because the data can come from simulation, experiments, as well as sensors. So if you talk about digital twin, which is a project we work in the ERC that Michael mentioned about, is data fusion problem. And lastly, the uncertainty propagation, quantification. In material area, we're using or developing a lot of technique that deal with microstructural analysis and the stochastic multiscale analysis, because all the material system, you can think about analysis involve multiple scale, from nano to meso to macro scale. So there's a problem about how do you propagate the variation, the microstructure. They are very much stochastic by nature, right? And that's weird, which is the reason I'm kind of feel a lot of opportunity in this area is the stochasticity. How do you propagate that kind of stochastity's impact of those stochasticity on the performance you're interested in? So today I'm going to cover some of those. I don't think I'm going to have time to do the last two topics, but I will show you some of the machine learning as well as adaptive discovery that we have been working on in the material system. So in general, this is a multidisciplinary problem. So I'm coming more from we call the design community. I think some of you here are working in this engineering design community. So, but together we have to work with people who are specialized in materials, mechanics, as well as manufacturing, because manufacturing has a huge impact on the material structure. And then the data science is something that brings us together these days, okay? So I'm going to bring up a few challenges in design from the design point of view. Three aspects: design representation, design evaluation, design synthesis. So design representation answers the questions about how do we describe our design space, right? So in this case, it's very high dimensional, and it's also mixed variable. I mentioned that some of them could be categorical, like whether I should use this element, or whether which kind of a surface treatment method I should use, processing technique. Some of them are deterministic, like if we use topology optimization, we can treat this as a deterministic problem where we design like each location where there should be black and white, right, or the density of the material. But on the other hand, we found actually stochastic method could be more efficient. We can use stochastic approach to describe those very complex morphology using only a few variables, small number of variables, and then we can do design. So that's the first research topic. The second one deals with design evaluation, which is all the like the analysis we do is physics-based. So there's a huge computational cost, and they're multi-physics, multi-model, so coming from different sources, as well as we want to know the impact of uncertainty. And the last one we call design synthesis, and you can think about this as just like design optimization, right? Optimization is a synthesis process. You set up objective, you search this space. So the big challenge is the vast design space. There's so many different options, multiple scale. Co-design means we're not only design material, architecture, or choice, and in some cases we need to design manufacturing process because they have an impact. It's a kind of nested problem. They have an impact on the structure at each location. Heterogeneity is a challenge, is also desirable. I will show you later on that higher performance, superior performance actually come from the fact that you want to make your system at different location, you want the structure to be different. So the heterogeneity also bringing another dimensional complexity, like each location, the structure can be different, right? And the resource allocation is a big problem. So we're using this paradigm called data-driven design, fuse information from different sources using statistical inference technique, like a GP, Gaussian process, as well as machine learning technique that could use like very high-end, like a deep learning kind of technique to do a closed loop discovery and the design automation. So at the end, we hope that human can have very little interference with the process and everything could be automated. So that's the kind of the research vision that we have there. So let me tell you a little bit about, I'm going to walk through 3 examples with you to give you some some brief idea about the different methods we're developing. I will start with nano composite design, which is very stochastic system, goes into a metamaterial design, which is a very deterministic kind of architectural design. And at the end, I will show you some recent work that we're getting into programmable material system, which makes system a dynamic problem. So we have to use dynamic optimization in order to solve this problem. So the problem is getting more and more difficult based on the dimensionality. So for the nano composite design, the challenge is mixed variables, lack of data, some data coming from experiments, multi-model, combinatorial. Okay, combinatorial means there's many different possibility of combination. So the methods I'm going to introduce is called LVGP, latent variable Gaussian process, as well as Bayesian optimization. So this work has been already finished, and I'm using an example that we're designing a nano dielectric material that could be used in the utility line, carry over the electricity, right? So the practical impact can be large, and we are designing this material so that it can have a good storage behavior. So this is from the dielectric point of view, insulation, good insulation, and then have good mechanical endurance. So this problem actually involves a lot of trade-off, because from the mechanical point of view, a stronger material is the one that you put in lots of those particles that basically it reinforce your material, make it stronger, okay? But too dense will have you are going to sacrifice your dielectric behavior, okay? So it's multifunctional, meaning multi-objective. On the other hand, we have decision we need to make, like what kind of polymer we should use, that's the base matrix, and what kind of surface treatment. So for polymer, we have PS, PMMA, and for surface treatment, we have 3 different choices. So those are the category variables that we talked about. At the design evaluation side, we have finite element simulation, very expensive because it needs to model the kind of the interface behavior between the particle and the matrix. And then we also have machine learning technique that use the data to build a model that relates the objective function. Here we have 3 objectives: breakdown strength, dielectric permittivity, and the dielectric loss. So we have to make a trade-off among those. So we're using this approach that I talked about early, which are just same slides. I just want to remind you that we are using this iterative method. But here with the challenge is we need to create a GP model which can capture the inputs. Some of them are categorical. So we developed this method, LVGP, first published 2020 in Technometrics, which is a statistical kind of a journal. And later on in the scientific report, we show the 3 material design examples. So let me kind of give you some idea of the behind this approach. So here we have inputs are both categorical and continuous, and we call category variable T, continuous variable X, and the response is Y. So let's just imagine the category could be the shape of our structure, okay? And we have 3 options: triangle, circular, and the square. So if we do not have a method that can take the category variable as input, we often look at what is the physical descriptors behind this kind of a concept, right? And that could be very high dimensional. So I'm using a diagram here to show that behind this concept, it could be very high dimensional category variables. And we don't often have this knowledge. So we're bypassing, our method of bypassing this descriptor, physical descriptor, we directly goes into, we create a new set of variable called the latent variable. So the latent variable Z, we found the 2 dimension would be sufficient. So traditionally, the GP model using the maximum likelihood function, right? To maximize that function, you can making sure your data match with your function prediction, okay? And it's based on the correlation. So here we're introducing Z as a new set of hyperparameter when we do this maximum likelihood function. And so we try to find the location of the Z, Z1, Z2 for each concept that we're interested in, or each level of the category variable. And here the distance has this meaning. When the distance is very close, it means that they're strongly correlated and they have similar impact on the response of interest. So in this case, it could be the material property. That's something we're interested in. And when the concepts are very far apart, that means that they're less correlated or their impact on the response is very different. So to some extent, we call this interpretable machine learning, right? It's using GP here for machine learning, can tell us how different those different levels are in terms of their impact on the response of interest. So this is supervised latent space, not in many other machine learning technique. When you hear this word, the latent variable, oftentimes it's unsupervised, right? So here it's a supervised. So this is a code that I think now we may have even more downloads. 2 years. I think this data was collected at least half a year ago. We have already like 18,000 downloads for this code. And it is very handy method for problem with mixed variable. And you can combine with GP directly because it provides uncertainty quantification everywhere for you, okay, in the space. And basically it maps a category variable to numerical variable in an implicit way. So we call this implicit mapping. So I'm going to show you a little bit about this, give you some sense using this example here. So we're designing the morphology. That's our continuous variable. So that's another research development in our work is using, we propose to use a spectral density function, which is a Fourier transformation to convert a very high dimensional structure design problem to a low dimensional design problem. So if you take a look, this complex structure now becomes a step function after you do the conversion. So you only have two variables, okay? And for this nanodielectric material, these are the images from my collaborator. So her lab actually can make those materials. So we change different process conditions, but doesn't matter how you change it. There's an underlying signature of a material system that can be captured by this spectral density function. So in this case, we find an exponential spectral density function with two variable theta. We call them dispersion parameter as well as a k, a constant, plus the volume fraction. And these three variables are sufficient to describe, in this case, actually two variables, theta and the volume fraction are sufficient to describe the differences of the dispersion status. And there's no restriction of the type of the particle shape. It could be very complex. It doesn't have to be circular, okay? So very low dimension, we can now design this morphology, okay, by converting this into a kind of a, we call the stochastic representation. So those are the two variables, plus the other category variable, like the polymer choice, as well as the surface treatment. So I'm going to show you some results. First, we compared the BO with genetic algorithm for this search. And we did this many replicates, over 10 replicates, because BO relies on the initial DOE you choose, right? So what are the first several sets of sample may have an impact on the end results. So we did it multiple times. So you can see GA performance, similar amount of sample is much less competitive compared to BO. So for this movie here showed you how the samples are chosen. So each of this is an iteration. We choose 1 point each iteration. And you can see that this is a multi-objective space. It's not a design space, it's the objective space, okay? So you can see these points, the initial ones are the blue color one, we call them random initial design. And the new ones are the black ones, and the green ones are the we call the Pareto design. So we actually use multi-response GP and the Pareto optimization to guide this search. As you can see from the movie, this method basically is able to travel through this two disjoint space. Okay, the sample, you can see that the iteration from one iteration to another, it is able to move around in this space. And if we take a closer look at what are the design behind this two space, everything on the top is the one that when the polymer is as PMMA, okay? And everything in the lower part is when the polymer is PS. So the polymer choice determined the kind of the space they are. On the other hand, for the Pareto solution, you can see the surface treatment could be very different based on what is your objective function at the end. How do you make a trade-off, right, of these three objectives? And based on the weights you give, you could end up with either this amino or nitron as some kind of different treatment. And the morphology could also be very different based on your trade-off between the mechanical as well as the dielectric property. I think I probably took away another slide to show you the latent space. The latent space also could show us the distance between those different methods, like surface treatment as well as the polymer choice. I think I have some other slides later on will give you more insights in this latent space, but let me go on to this, going into the second problem I want to share with you. The type of problem is metamaterial design problem, okay? So here the design, the challenge here is that we are actually building library of different unit cell design. And so the data quality issue about how we choose the data, how we generate the data. And it is a multi-scale problem because we are designing heterogeneous material system that the unit cell can be different at the different locations. So the method that we're using, we are again using LVGP, and I'll show you this latent variable GP can play an important role in this kind of architecture design problem, because now we can treat the different type of architecture as a category variable, okay, in the machine learning. And then we're combining machine learning with topology optimization. So I think the contribution here is that we are maybe one of the early group really not just using machine learning to create the architecture design for unit cell. We're looking at its benefits in the multi-scale design context. So I will show you some strategy we use to do multi-scale problems. So first, what is metamaterial system, right? And many of you may be familiar with it. Some of you, maybe this is new to you. So metamaterial system actually have a lot of usage potentially in mechanical system. So this is called a system with negative Poisson ratio, right? When you compress, when you extend, that it has an interesting phenomenon in terms of whether it will shrink or it will expand. So this kind of system could actually be used in surgical situation like the stent surgery. Like you like to design this system here that it is strong enough, okay? At the same time, when there is this like blood flow flowing through this, it needs to kind of blow, okay? So it's like a spring, you can imagine, right? Designing a spring structure is a super difficult problem. If you work in this metamaterial area, it needs to be flexible, right? But also need to be very strong. So how do you design this kind of architecture? And in civil engineering, there are examples. Actually, these days, people are designing the highway or concrete in some kind of following some architecture so they can observe the energy from vibration. And the vision is to transfer them into energy, then can power like a sensor, okay, in the car. So I would think this is still a research topic. Like there are many good design these days, but how do you use it in real system? There's some good examples these days, but not many. So this is still very much a growing research field, metamaterial design. So, and I know some of you are interested in soft robot system, and I want to use this as a motivation problem to demonstrate why do we need to design system are heterogeneous, okay? So in order for a soft robot to deform in the way you design, actually, you need to design the structure that the stiffness is different at different locations, okay? So how do we achieve different stiffness at different locations, right? And one solution is to change the material, right? But that means you need to put different material at different location. Another solution is change the architecture, because the architecture has the structure has a direct impact on the property, basically, right? So based on this chain of relationship. So this is an example of the system with negative Poisson ratio. You can see that, when you apply load, like how it deforms, it has some interesting behavior. In general, a system with negative Poisson ratio can lead to very good energy absorption behavior. So you can imagine you design a bumper, right? Or hammered, like those structures are very desirable because they can absorb the energy. So in our research, we're looking at a building block concept that we're creating database of different architecture. And then we kind of use this information to build very complex system. that follows a heterogeneous architecture. Okay, so that's the difference between our research and some of the other machine learning work that only looking at the unit cell design. So now what you can imagine is that you are designing a butterfly. We call this multiscale topology optimization. You're not only just designing the wing shape of this butterfly, like, based on the maybe aerodynamic performance, you're also designing at each location, what is the best architecture? Okay, so each of those unit cell of the wing, the architecture can be different. So it's a multi-scale problems. And in the past, in the topology optimization community, like topology optimization is a method, start with a block of material, and it can converge to the solution if you say, I want 20% reduction or 30% weight reduction, right? This is topology optimization, and it is a method. Some people call this, it's actually a revolutionary method, okay, to change the design, structure design problem. And also it takes advantage of additive manufacturing, right? So topology optimization has an interesting history. It was very active topic back to, I think, University of Michigan has Professor Kikuchi, that was almost 30 years ago, developed this method, but then it cooled down a little bit. Nobody cared that much. Now it's kind of booming again because of additive manufacturing. So there's very close relationship with manufacturing. But the problem with topology optimization method, the current one in the software, in the commercial software, it assumes the material is the same everywhere. Okay, you use the same material, like for this structure. But now we're talking about the material could be different at each location, right? So how do we design this? And the manufacturing technique also made this possible. You can have very different material at different locations, additive manufacturing. So we're kind of developing this method based on data-driven approach, building a library of different architecture, looking at their impact on the property. So the property is a matrix. Okay? It's not a single property. For 2D, for 3D, right? You can have this C11, C12, so it's multiple dimensional. So I'm going to show you how we use data-driven methods, and we follow a loop we call acquire, gathering data, learn, and generate. So that is the place we use heavily machine learning technique and GP methods, and the final rate is optimize. Okay, optimize is a system level decision making. We put them together, but this is very iterative. Like even the step of data acquisition, we strongly recommend to take into account optimization objective at that stage to think about the the data quality. And we're also using methods of machine learning technique to understand interaction between different aspects like material, architecture, and for programmable material system, we can add another circle in the middle, that's the stimuli. So we're looking at the interaction using machine learning technique. So a little bit about the data quality. In this case, you can think that you have two space, okay? One is the design manifold space that you can generate a lot of different architecture, right? Based on like spring nodal design, lattice structure, isosurfaces. Those are structure generated by totally different methods or different representation. So they're different location design manifold. But in the property space, they overlap hugely. Okay, there's overlap between all these different. So how do we understand this kind of relationship, right? Can we build a unified space for multi-class unit cell structure? Can we go beyond that's the top question in design, is go beyond the existing property, right? You want to go somewhere that you never had any existing design before. So we did a developing method called task-aware data acquisition, and this is work from Doxo, who recently defended his thesis, and the paper was a best paper a couple of years ago, 2 years ago in the IDTC. So the topic here is that the data itself, the geometry, there's no cost. We already have, we can gather, like here, 88,000, like a library of architecture, right? The cost is about simulation, simulate its property. So how do we decide what data we choose from this library so that we can accomplish the property we want? So in this case, we design, in the structure design, this anisotropic property that C11, C22 is designed to have a huge differences, not on the diagonal. We want to push the points, okay, toward its boundary. So what you see here the boundary, the line there is like the physical restriction. You can never go beyond that boundary, okay? So we're developing data sampling technique. It's information-centric. There's entropy idea, there's uncertainty methods involved that using active learning to sample the data. So here you can show random simulation, and we also apply a metric called the diversity metric. Diversity metric measure the difference between the geometry as well as the diversity in the property, okay? And those metrics together. So at the end, combining both diversity and the quality metric, you can see now this is the distribution of the data. They can see those are two different peaks, right? Because we want to push the data towards the two end. So this two end represent two different peaks. So uniform sampling is never the best if you think about you have a design goal there, right? You want to guide the sample toward the goal. So that's one example of the work we work on the data quality issue. This paper is recently released online. It is a review paper. Take us almost 2 to 3 years with all the students working together, publishing advanced materials on a literature survey on data-driven design for metamaterials and the multi-scale systems. I highly encourage you to look at this paper. And this is a picture in a session where we talk about machine learning. And what is interesting here, to break down the paper into what are the kind of physical functionality, right? Mechanical, acoustic, optical. There's a lot of optical application. Design scenario, meaning are you able to allow, or do you want a method which is iteration free? Like if you think about machine learning, right? Many of the technique like generative modeling technique, you can do inverse design without any iteration, right? You give the targets, you find what is corresponding geometry. So we call this iteration-free inverse design. And some other methods fall into iterative design optimization, even though they use machine learning, right? Here is the last column is machine learning technique, okay? And some of those methods still need to use iterative algorithm after you build the machine learning model, okay? But some of those methods can do iteration-free inverse design. So GP is not shown as a very widely used method. And the reason is because GP usually can only handle small number of inputs, like 20, 30, right? But this is a problem with very high dimension, right? But in our work, we actually use LVGP to get around with that. And I will show you how we use LVGP. So the most widely used machine learning technique here, many of them are generative approach. So DGM is generative machine learning methods. So there's many different techniques, and another is focus, whether they're looking at one-to-many mapping, because design is never one-to-one, right? There could be one-to-many, okay? And then there are other different methods. So this is a very good picture that captured the current, in the literature. I think the journal, this review article includes close to about 400 400 papers in this area. What is generative modeling, right? Generative modeling, we have also used this in our work. It's very good for problem that you want to create free-form geometry because it's very high dimensional. So here you can see we train some existing data. We can generate new design, right? Based on the training set. So there is encoder, decoder. There is this mapping that doesn't really need any iteration. So this is approach here. On the left, you can see giving a target in the property space, we'll know the geometry directly. But in some cases, it still needs some iteration to find the solution.
Okay, wait.
Yeah.
This is very interesting, but if we want to leave some time for questions,
yeah,
maybe we can wrap up in 5 minutes or so.
Okay, yeah, okay. I will leave 5 minutes for questions, okay? And we are also using generative modeling to quantify the uncertainty. So basically, this is a case we use a hierarchical deep generative model, okay, to quantify the uncertainty. So now with the data set of different fabrication data set, in the future, when we do design, by specifying the nominal design, we can predict what's uncertainty that's associated with manufacturing imperfection. So I will quickly wrap up by showing just two strategies. One is top-down, that we use topology optimization, the highest level, to optimize property. rather than architecture. And then we retrieve the library to assemble them together, okay, to come up with an architecture. Another is bottom up, where we use LVGP to build the machine learning model, GP model, has category variable as inputs, and then passing the information to the top layer, then put into topology optimization. So it's integrated with topology optimization rather than only use machine learning. So the LVGP method is here's an example how we design compliant structure that by choosing different material, blue and the red, and also different architecture. There are 8 different architecture. And this is the initial design. This is the final design. The compliant mechanism, the goal is to achieve the largest displacement. Okay. So here you can imagine we're building a library of a different class of architecture, material, and build this LVGP model, the latent variable GP model, together with volume fractions, continuous variable. So this is the data set. And the latent space tells us how similar or different of this architecture with respect to the impact on the property. So, and for the increasing the flexibility, this is where we use generative modeling. We are able to do this functional graded structure because now we have a generative model can travel from different class of material, right? This class, that class, in between, there's a continuous model there. It's called the generative model there that can allow us to design this in a functional graded way to mitigate the impact from manufacturing. And we can also change the angle. And for the top-down method, the idea is to design the target first. So I'm kind of quickly clicking through this. We're optimizing the property at each location, C11, C22, and then we retrieve the library to build the architecture that meets this property. So that's a top-down method, and we did an experiment on this. And this is, you can put in any shape, like you can imagine this is a packaging problem, like you pack a Mickey Mouse, and it's called a string cloaking device, that you don't want the displacement of this different from you if you don't have an object in the middle. Okay, it's called the string cloaking. It's a very challenging design problem, so we used this method. So I'm going to skip the programmable material system of the top. Programmable materials, we're adding stimuli. It's a dynamic optimization problem now. And I will just go directly to the end of the talk, just to kind of summarize that I showed one example of the nano composite where the design representation is very critical, that we really want to identify small sets of design variable to address the system, design system, which is stochastic. The mixed variable GP is used there. And in the metamaterial example, I showed that the data quality is very important, and we can use a multiscale strategy to address the heterogeneity. And the last one didn't have chance to show is the problem that you have a stronger interplay between material, structure, and the stimuli. So, and for this kind of dynamic programming problem, we're using differentiable methods. These days, there's a lot of differentiable simulation approach coming up, and it's very critical for design this kind of system because it allows us to get gradient information without doing analytical derivation. That's super important for topology optimization, and we found more and more use of those kind of approach for design programmable materials. So I think I will just end there and just take any questions that you may have.
Thank you.